Imagine standing before the Pantheon in Rome on a misty morning in 126 AD. The massive concrete dome stretches impossibly high above you, its perfect proportions defying everything you thought you knew about ancient construction. How did Roman architects, working with nothing but bronze tools, wooden scaffolds, and human ingenuity, create structures that still stand nearly 2,000 years later? Tonight, we'll journey back to witness one of history's greatest architectural mysteries unfold, as master builders transformed raw materials into eternal monuments using techniques that would astound modern engineers. Marcus Claudius Severus wiped the sweat from his brow as he surveyed the construction site that would soon become the greatest architectural wonder of the ancient world. The year was 118 AD, and Emperor Hadrian had just commissioned him to rebuild the Pantheon, not just repair it, but completely reimagine it as a temple that would surpass every structure Rome had ever built. The morning sun cast long shadows across the forum, where hundreds of workers were already hauling massive blocks of travertine limestone, their voices echoing through the streets as they called out measurements and directions in a dozen different languages. Severus was no ordinary architect. Born in Alexandria to a Greek mathematician and a Roman engineer, he had spent his youth studying the great monuments of Egypt, and his adulthood perfecting the revolutionary building techniques that were transforming the Roman world. At 43, he commanded the respect of stonemasons from Britain to Syria, and his innovative use of concrete had already changed the skyline of Rome forever. But the Pantheon would be different. Hadrian had made it clear that this wasn't just another temple. It was to be a statement about Roman engineering prowess that would endure for millennia. The challenge seemed impossible. The emperor wanted a dome larger than any ever attempted, a perfect hemisphere that would seem to float weightlessly above the temple floor. No wooden supports could span such a distance. No stone arch could bear such weight without massive buttresses that would destroy the building's elegant proportions. But Severus had a secret weapon: Roman concrete, a revolutionary material that most of the world had never seen. Walking through the crowded streets of Rome that morning, Severus made his way to the lime kilns outside the city walls, where crews worked day and night producing the cement that would bind his vision together. The secret lay in volcanic ash from the Bay of Naples, a gray powder that, when mixed with lime and water, created a stone harder and more durable than anything nature had produced. The Romans called it pulvis pudiolanus, and it was about to change architecture forever. The discovery of this miraculous material had come decades earlier, when Roman engineers building harbor works at Puteoli noticed that mortar made with local volcanic ash set under water and actually grew stronger with time. Unlike traditional lime mortar, which dissolved in water, this new cement seemed to thrive in wet conditions. Engineers across the empire began experimenting with different volcanic ashes, discovering that each deposit had unique properties that could be exploited for specific construction challenges. The construction process began not with the famous dome, but with foundations that descended deep into the marshy ground near the Campus Martius. Teams of slaves and freedmen dug through layers of ancient debris, Roman pottery shards, and forgotten building stones until they reached solid clay 20 feet below street level. Here, Severus's crews laid a foundation ring of travertine blocks, each one precisely cut and fitted without mortar, their weight alone sufficient to anchor the enormous structure above. The foundation work revealed the sophisticated understanding Romans had developed about soil mechanics and structural loads. Severus knew that the Pantheon's enormous weight, over 9,000 tons when completed, would slowly settle into the soft Roman soil unless properly distributed. The foundation ring was therefore designed not as a simple platform, but as a complex system of interlocking stones that would spread the building's weight over the largest possible area while preventing uneven settling that could crack the walls above. But what made Roman construction truly revolutionary was their systematic approach to materials and measurement. In workshops scattered throughout the city, master craftsmen were already preparing the thousands of components the Pantheon would require. Brickmakers shaped millions of triangular tiles from clay dug along the Tiber River, each one fired at exact temperatures and marked with the potter's stamp to ensure quality control. These weren't random bricks, but precision-made components designed to specific dimensions and load-bearing requirements. The Roman system of standardized measurements ensured that bricks made in one workshop would fit perfectly with those made in another. The basic unit was the Roman foot, divided into 12 inches, but builders also used specialized measuring tools calibrated for specific construction tasks. Bronze squares ensured perfect right angles, while plumb bobs and levels made from water-filled bronze tubes guaranteed that walls rose straight and true. Stonecutters worked massive blocks of travertine from quarries near Tivoli, using bronze chisels and wooden wedges to split the limestone along its natural grain with precision that would impress modern quarry workers. The bronze workers faced perhaps the greatest challenge of all. The Pantheon's massive doors would weigh over 20 tons each, and the bronze nails and fittings had to be cast to tolerances that would be impressive even by modern standards. In foundries filled with roaring furnaces, master metalworkers melted down, captured enemy weapons and old bronze statues, adding precise amounts of tin to create an alloy that would neither rust nor weaken over time. The casting process required intimate knowledge of metal behavior. Too much tin and the bronze would be brittle, too little, and it wouldn't flow properly into the intricate molds. Roman bronze working had reached extraordinary levels of sophistication by Hadrian's time. The great doors of the Pantheon required not just massive amounts of metal, but incredibly precise engineering to ensure they would hang properly and operate smoothly despite their enormous weight. The hinges alone were marvels of ancient engineering, designed with bronze bushings and carefully calculated leverage points that allowed a single person to open doors that weighed as much as a modern truck. As summer turned to autumn in 118 AD, the first courses of the Pantheon's walls began to rise. Severus employed a building technique that perfectly demonstrated Roman engineering genius. The walls weren't built of solid stone, but of concrete poured between thin layers of brick. This opus mixtum construction was lighter than solid masonry, stronger than pure concrete, and could be built much faster than traditional stone construction. The technique also allowed for much more complex internal spaces. Roman builders could create curved walls, vaulted ceilings, and intricate architectural details that would have been impossible with stone block construction. The concrete itself was a marvel of ancient chemistry. Roman cement makers had discovered that volcanic ash from different locations had different properties. Ash from Pozzuoli created concrete that could set underwater, while ash from the Alban Hills produced an especially hard mixture perfect for load-bearing walls. For the Pantheon, they used carefully tested combinations, adding crushed pottery and brick dust to create a concrete matrix that would actually grow stronger over time as the volcanic ash continued to react with lime in the presence of moisture. The mixing process was as important as the ingredients themselves. Roman builders understood that concrete had to be mixed in specific proportions and used within a limited time after mixing. They developed standardized measuring vessels and mixing techniques that ensured consistency from batch to batch. The work was typically done by teams of slaves supervised by experienced foremen who could judge the quality of a mix by its color, consistency, and the sound it made when stirred. But perhaps the most ingenious aspect of Roman concrete construction was their use of aggregate, the stones and rubble mixed into the cement. Rather than using random debris, Roman builders carefully selected their aggregate based on weight and structural requirements. At the base of the Pantheon's walls, they used heavy travertine chips and basalt fragments to provide maximum strength. Higher up, they switched to lighter materials, tufa stone, then broken pottery, and finally, in the dome itself, pumice stone that was so light it could float on water. This graduated use of aggregate wasn't just about reducing weight. It was a sophisticated understanding of how different materials behaved under stress. Heavy aggregate at the base provided a solid foundation and helped resist the outward thrust of the dome above. Lighter aggregate higher up reduced the total load while maintaining structural integrity. The pumice used in the dome's upper sections was specially selected from volcanic deposits near Naples, where centuries of eruptions had created vast beds of naturally lightweight stone. The wooden scaffolding required for the Pantheon's construction was itself an engineering marvel. Master carpenters designed a framework that could support not just workers and materials, but the enormous weight of wet concrete as it cured. These temporary structures required thousands of pine logs from the forests of northern Italy, precisely joined with bronze nails and wooden pegs into frameworks that rose over 140 feet above the temple floor. Roman carpenters had developed sophisticated joinery techniques that allowed them to create incredibly strong wooden structures without using iron nails, which were expensive and prone to rust. Instead, they used carefully shaped wooden joints, mortise and tenon, dovetails, and complex interlocking systems that actually grew stronger under load. The scaffolding for the Pantheon incorporated elements borrowed from shipbuilding, siege engine construction, and architectural frameworks, creating hybrid structures that could bear enormous loads while remaining stable in wind and weather. The carpentry work also had to account for the natural movement of green timber as it dried and seasoned. Roman builders understood that wooden structures would shift and settle as the wood lost moisture, so they designed joints and connections that could accommodate this movement without losing strength. The scaffolding systems used wedges and adjustable components that could be tightened or loosened as needed to maintain structural integrity throughout the construction process. As the walls rose higher, Severus faced a problem that had stumped architects for centuries: how to create window openings in concrete walls without weakening the entire structure. The solution came from studying the principles of the arch. By embedding wooden frames in the concrete and removing them once the mixture had cured, Roman builders could create perfectly shaped openings that actually strengthened the wall by redirecting structural loads around the opening. This technique, known as void forming, required extraordinary precision in the placement and removal of wooden forms. The forms had to be strong enough to resist the pressure of wet concrete being poured around them, yet removable once the concrete had cured. Roman carpenters developed specialized tools and techniques for extracting these forms without damaging the surrounding concrete, often using tapered designs that could be driven out with bronze wedges once the concrete had hardened. The architectural details of the Pantheon's interior required even more sophisticated forming techniques. The great coffers that decorate the dome's interior surface weren't just decorative. They served crucial structural and practical functions. Each coffer reduced the weight of the dome while creating a pattern of reinforcing ribs that helped distribute structural loads. Creating these complex three-dimensional shapes required wooden forms that were essentially reverse sculptures, precisely carved to create the desired interior spaces. The year 120 AD brought the greatest challenge of all: construction of the dome. No structure of this size had ever been attempted, and even Severus wasn't entirely certain his calculations were correct. The dome would span 142 feet, weigh over 5,000 tons, and somehow had to support itself without any internal pillars or external buttresses. The secret lay in the Roman understanding of structural forces, and their masterful use of the arch principle extended into 3 dimensions. Construction began with a massive wooden framework built from the ground up. This centering, as it was called, was essentially a complete wooden dome that would support the concrete until it cured and became self-supporting. The framework required over 200 tons of seasoned timber, all cut to precise curves and joined with bronze fittings that could be disassembled once the concrete had hardened. The curves had to be mathematically perfect. Any deviation would create weak points where the concrete might crack under its own weight. Roman carpenters used a technique called striking the centers to create these perfect curves. Starting with a central point at the base of the dome, they used bronze compasses with extended arms to scribe perfect arcs on the wooden framework. Each piece of timber was then cut to follow these curves exactly, creating a structure that was geometrically perfect despite being built entirely by hand with bronze tools. The wooden centering also had to be designed for easy removal once the concrete had cured. Roman engineers developed ingenious systems of wooden wedges and adjustable supports that could be lowered gradually, allowing the concrete dome to settle onto its own structure without sudden shock loads that might cause cracking. The removal process required careful coordination among dozens of workers, all following precise procedures developed through centuries of trial and error. The concrete for the dome was mixed in small batches and poured in layers, with each layer allowed to partially cure before the next was added. This prevented cracking from uneven shrinkage and allowed the builders to adjust the mixture as they worked higher. At the base of the dome, they used their heaviest concrete, loaded with travertine aggregate. Gradually, As the dome curved inward, they switched to lighter mixtures, until at the very top they were using pumice so light that the concrete would actually float. The layered construction technique, known as lift work, required extraordinary coordination and timing. Each lift had to be completed in a single day to ensure proper bonding between layers, which meant that hundreds of workers had to maintain a steady pace of mixing, carrying, and placing concrete for hours at a time. The work gangs were organized with military precision, with experienced foremen stationed at key points to monitor quality and coordinate the flow of materials. Roman builders also understood the importance of curing conditions for concrete strength. They developed techniques for keeping concrete moist during the critical early days of curing, using wet cloths, standing water, and even steam from heated pots to maintain proper humidity levels. The chemistry of Roman concrete was such that it continued to gain strength for months or even years after placement, but only if proper curing conditions were maintained during the first few weeks. But the dome's most famous feature, the great oculus or eye that opens to the sky, wasn't just an aesthetic choice. This 27-foot opening at the dome's peak serves a crucial structural function, reducing the weight at the point of maximum stress while providing perfect balance to the forces pressing outward from the dome's base. Rain falling through the oculus drains away through nearly invisible channels built into the floor, a detail that demonstrates the Romans' attention to every aspect of their building's performance. The oculus also solved a critical construction problem: how to finish the top of a concrete dome. Traditional masonry construction could simply place a capstone at the highest point, but concrete domes created enormous compression forces that had to be carefully managed. By leaving the oculus open, Roman engineers eliminated the most difficult part of the construction while creating a feature that enhanced both the building's structure and its spiritual significance. The drainage system for rainwater entering through the oculus was a masterpiece of hydraulic engineering. Nearly invisible bronze drains were built into the marble floor, connected to a complex system of pipes and channels that carried water away without any visible impact on the building's interior. The floor itself was slightly domed, sloping almost imperceptibly toward the drainage points to ensure that even small amounts of water would flow away efficiently. The construction techniques used for the Pantheon's interior were equally sophisticated. The great columns supporting the portico were single pieces of granite, each one weighing over 60 tons and transported from quarries in Egypt. Moving these monoliths required specially built ships, reinforced roads, and rolling systems using bronze balls and wooden tracks that distributed the enormous weight. The precision required to position these columns was extraordinary. They had to be perfectly vertical and aligned to within inches over their entire 40-foot height. The logistics of moving Egyptian granite columns to Rome involved some of the most ambitious transportation projects of the ancient world. Special ships called obelisk carriers were built specifically for transporting massive stone blocks, with reinforced hulls and specialized loading equipment. The journey from Egyptian quarries to Rome could take months, with stops required for weather and the complex process of transferring cargo between different types of vessels as the stones traveled up the Nile, across the Mediterranean, and up the Tiber River to Rome. Once in Rome, the columns had to be moved from the river docks to the construction site using techniques that pushed the limits of ancient engineering. Roman builders used systems of bronze rollers, wooden tracks, and teams of oxen to move loads that weighed as much as modern railroad cars. The process required careful route planning to avoid steep grades and narrow streets, sometimes necessitating the temporary removal of buildings or the construction of special roadways to accommodate the massive stones. The precision required for positioning these enormous columns was achieved using techniques borrowed from Greek temple construction but refined by Roman engineering. Bronze measuring instruments, water levels, and geometric calculations ensured that each column was placed exactly where the architect intended. The columns had to support not just their own weight, but the enormous loads imposed by the structure above, requiring foundation work that extended deep below the visible floor level. The marble veneer that covers the Pantheon's interior walls demonstrates another aspect of Roman building genius: the ability to make expensive materials go much further through skillful application. Rather than building with solid marble blocks, Roman craftsmen cut thin sheets of colored marble and attached them to the concrete walls with bronze clamps. This technique, called opus sectile, allowed them to create intricate geometric patterns using rare marbles from quarries across the empire: yellow marble from North Africa, purple porphyry from Egypt, and green serpentine from Greece. The marble cutting and installation process required skills that took decades to master. Roman stoneworkers used bronze saws with abrasive sand to cut marble sheets to exact dimensions, a process that was both time-consuming and expensive. The sheets had to be perfectly flat and smooth, with edges cut to precise angles that would create seamless joints when installed. Any errors in cutting or measurement would result in visible gaps or misaligned patterns that would mar the building's appearance. The installation process was equally demanding. Each marble sheet had to be carefully positioned and secured with bronze clamps that were hidden within the joints between stones. The clamps themselves were precision-made components, cast to exact dimensions and designed to hold the marble securely, while allowing for the slight thermal expansion and contraction that occurs with temperature changes. The skill required to install these systems without visible fasteners or support structures represented the pinnacle of Roman stoneworking technology. The mathematical precision behind the Pantheon's design would impress modern engineers. The dome's diameter equals the building's height, creating perfect proportional harmony. The thickness of the dome decreases from 21 feet at the base to just 4 feet near the oculus, with the reduction calculated to maintain structural integrity while minimizing weight. The positioning of decorative elements follows geometric principles derived from Greek mathematics, while the structural engineering relies on Roman empirical knowledge gained from centuries of building experience. Roman mathematical understanding, while different from modern calculus-based engineering, was remarkably sophisticated in its practical applications. Roman architects used geometric principles and proportional systems that had been refined through generations of building experience. They understood concepts like load distribution, structural redundancy, and the relationship between span and thickness that are fundamental to modern engineering, even though they expressed these concepts in geometric rather than mathematical terms. The proportional systems used in Roman architecture were based on modules and ratios that created naturally pleasing relationships between different parts of a building. The Pantheon's design incorporates the golden ratio, perfect geometric shapes, and proportional relationships that create a sense of harmony and balance that visitors still experience today. These weren't arbitrary aesthetic choices, but carefully calculated design decisions based on centuries of architectural experimentation and refinement. As the Pantheon neared completion in 125 AD, the final challenge was removing the enormous wooden framework that had supported the dome during construction. This process, called striking the centering, was perhaps the most nerve-wracking moment in the entire project. If the concrete hadn't cured properly, or if Severus had miscalculated the structural loads, the dome would collapse the moment its wooden support was removed. The striking began at dawn on a windless day in early spring. Teams of workers simultaneously removed wooden wedges from dozens of support points, allowing the framework to settle and separate from the concrete above. Hour by hour, more supports were removed until finally the dome stood free, supported only by its own carefully calculated structure. Contemporary accounts describe crowds gathering in the streets as word spread that the impossible had been achieved. A dome larger than any in history was standing on its own, defying gravity through human ingenuity alone. The moment when the wooden centering was finally removed represented not just the completion of a building, but the validation of centuries of Roman engineering development. Every technique used in the Pantheon's construction had been tested and refined in smaller projects across the empire. The successful completion of the dome proved that Roman engineering had reached a level of sophistication that wouldn't be matched again for over 1,000 years. The techniques used to build the Pantheon weren't limited to this single masterpiece. Across the Roman Empire, local builders adapted these methods to construct aqueducts that carried fresh water across hundreds of miles, amphitheaters that could seat 50,000 spectators, and basilicas that would later inspire the great cathedrals of medieval Europe. The principles of Roman concrete construction spread to Britain, where they built Hadrian's Wall, to Germany, where they constructed heated bathhouses, and to North Africa, where they created vast granary complexes that fed the empire. The spread of Roman construction techniques throughout the empire was facilitated by a sophisticated system of technical education and knowledge transfer. Experienced architects and engineers traveled constantly, supervising major projects and training local craftsmen in the latest techniques. The Roman military also played a crucial role in spreading construction knowledge, as legionary engineers built roads, bridges, and fortifications that incorporated the most advanced techniques available. Roman technical manuals and treatises, like Vitruvius's De Architectura, codified construction knowledge and made it available to builders throughout the empire. These texts included not just theoretical principles, but practical instructions for everything from site preparation to material selection to quality control procedures. The standardization of techniques and materials across the vast Roman Empire ensured that a building constructed in Britain would use the same basic methods as one built in Syria or North Africa. What made these achievements possible wasn't just technical knowledge, but an entire civilization organized around monumental construction. Roman society had developed specialized trades, standardized measurements, and quality control systems that ensured materials and techniques remained consistent across vast distances and long periods of time. The Collegium Fibrorum maintained standards for everything from brick dimensions to mortar consistency, while imperial architects like Severus traveled constantly, supervising projects and training local builders in the latest techniques. The Roman building industry represented one of the ancient world's most sophisticated examples of organized technological activity. The industry employed hundreds of thousands of workers in specialized roles: quarry workers, lime burners, brickmakers, carpenters, stonemasons, bronze workers, and dozens of other trades. Each trade had its own guild system, apprenticeship programs, and quality standards that ensured consistent results across the empire. The economic impact of Roman construction was enormous, driving demand for materials and labor that supported entire regions of the empire. Egyptian granite quarries employed thousands of workers, while volcanic ash mining near Naples created a major industry that supplied cement materials throughout the Mediterranean. The transportation networks required to move building materials stimulated the development of better roads, larger ships, and more efficient loading and unloading techniques. The Roman approach to construction also demonstrates their practical genius in logistics and project management. Building the Pantheon required coordinating the work of thousands of people: quarry workers in Egypt, lime burners outside Rome, bronze founders in specialized workshops, and hundreds of skilled masons and carpenters on the construction site itself. Materials had to arrive in precise quantities at exactly the right time, weather delays had to be anticipated and planned for, and the entire enormous project had to be completed within the budget and time frame demanded by an impatient emperor. Roman project management techniques included sophisticated scheduling systems, quality control procedures, and risk management strategies that wouldn't be out of place on modern construction sites. Project managers tracked material deliveries, monitored work progress, and maintained detailed records of costs and schedules. They developed contingency plans for weather delays, material shortages, and technical problems that might arise during construction. The financial management of major Roman construction projects required banking and accounting systems that were remarkably advanced for their time. Imperial building projects often required funding from multiple sources: imperial treasury, local taxes, private donations, and tribute from conquered territories. Project managers had to maintain detailed accounts, manage cash flow, and ensure that funds were available when needed for material purchases and worker payments. Perhaps most remarkably, the Romans achieved all this without the mathematical tools we consider essential for modern construction. They had no mechanical calculators, no steel measuring tapes, no power tools or heavy machinery. Instead, they relied on geometric principles learned from Greek mathematics, empirical knowledge gained from centuries of building experience, and quality control systems that caught errors before they could compromise structural integrity. Roman measuring and calculation techniques were based on geometric principles and practical experience rather than abstract mathematics. Builders used bronze instruments, water levels, and proportional systems to achieve precision that matched or exceeded what we expect from modern construction. The absence of mechanical aids was compensated by extraordinary skill and attention to detail that was developed through years of apprenticeship and hands-on experience. The quality control systems developed by Roman builders ensured that construction errors were caught and corrected before they could compromise a project's success. Master craftsmen regularly inspected work in progress, using standardized tests and measurements to verify that materials and workmanship met established standards. These systems prevented the accumulation of small errors that could lead to major structural problems in completed buildings. The legacy of Roman construction techniques extends far beyond the monuments that still stand today. Medieval builders rediscovered Roman concrete recipes and used them to construct Gothic cathedrals. Renaissance architects studied Roman proportional systems and applied them to palaces and churches. Even modern engineers marvel at Roman achievements. The Pantheon's dome was the largest concrete span in the world until the 20th century, and many Roman bridges and aqueducts are still in daily use after nearly 2,000 years. The rediscovery of Roman construction techniques during the Renaissance sparked a revolution in European architecture that produced some of history's greatest buildings. Architects like Brunelleschi studied Roman ruins to understand the principles behind their construction, then applied these lessons to create masterpieces like the Dome of Florence Cathedral. The influence of Roman architecture can be seen in buildings from the U.S. Capitol to the British Museum to countless churches, courthouses, and civic buildings around the world. Modern concrete technology still relies on principles first developed by Roman engineers. The use of pozzolanic materials, aggregate gradation, and reinforcement techniques all have their roots in Roman construction practices. Contemporary architects and engineers continue to study Roman buildings to understand how they have survived for so many centuries, often discovering principles that can be applied to modern construction challenges. As we drift toward sleep tonight, imagine Marcus Claudius Severus standing in the completed Pantheon on a warm afternoon in 126 AD. Sunlight streams through the great oculus, moving across the marble floors as the earth turns. The impossible dome soars overhead, its perfect curve seemingly weightless despite the thousands of tons of concrete and stone that form its structure. In achieving this miracle of engineering, Severus and his fellow builders had proven that human ingenuity, careful planning, and masterful technique could create monuments worthy of the gods themselves, monuments that would inspire and mystify viewers for millennia to come. The whispered conversations of visitors echo softly in the great space, mixing with the distant sounds of Roman street life filtering through the bronze doors. Somewhere in the city, new projects are already beginning, baths and basilicas, temples and theaters that will carry forward the techniques perfected here. The Roman Empire may eventually fade, but the principles discovered by builders like Severus will endure, testament to human creativity and the eternal desire to build something lasting from stone and dreams. In the gathering dusk of that ancient day, as oil lamps begin to flicker in the streets of Rome, the Pantheon stands complete, a perfect fusion of engineering and artistry that will outlast empires and inspire builders for thousands of years to come. The techniques that created this masterpiece, developed through centuries of patient experimentation and refinement, represent one of humanity's greatest technological achievements, proving that even without modern tools, human ingenuity can create wonders that touch the divine.